I'm Rinus Roelofs, a sculptor. I'm from Holland. I'm living in Hengelo. Yes, I'm a sculptor, but before I went to the School of Arts, I studied mathematics for a couple of years. And I stopped studying mathematics, not because I didn't like it, but I had the feeling that I could say more about mathematics to other people when I went to the arts. So my art is mainly about my fascination about mathematics. Yeah, I want to make clear that we didn't discuss our talks, but also I will start with some mathematics, and it has many connections with what the former speaker told about mathematics. I want to start with this theorem and this formula. Don't be afraid, this is the only formula I will use in my talk, so it's a very simple one, but therefore a very beautiful one. And one of the beautiful things is that when you restrict yourself to natural numbers, you will find that this is a solution of the equation. And this is really beauty. Well, I think you will agree. And it is also beautiful because when you look at the possible solutions of this equation, you will find that there are infinite many solutions with natural numbers. And to understand this a little bit more, I want to concentrate on the pattern of the numbers. So not only the numbers, but the patterns you can find in the set of the numbers. So starting with just the series of natural numbers, I add another series, the series of squares. And this series, 1, 2, 3, it goes up very slowly, and this goes up very quickly. But when you look at this series a little bit closer, you will see that the difference between each of the two numbers, in this case, the difference between 4 and 1 is 3. But for the complete series, you will find the difference between 4 and 9 is 5, 9 and 16 is 7. So this is a subset which is just the odd numbers. And this is interesting because in the series of odd numbers you will find a square, number 9. And this 9 is the difference between 16 and 25, but these numbers are all squares. So this is a way to find a solution of the Pythagorean theorem. And, well, 9 and 16 is 25, or 3 square plus 4 square is 5 square. So you can go on, going down this series of numbers, you will find a next square. So this is a next solution of the Pythagorean theorem. This is the difference between 144 and 169. So 5 square plus 12 square is 13 square. And it gives you another look at the series of numbers. You see a certain pattern, and now you see that you can find infinite many solutions of the Pythagorean theorem. Because you can go down in this series, and you will always find a next odd number, which is a square. And so this square, 7 square, is the difference between 24 square and 25 square, as you see here. So, starting with just the simple theorem of Pythagoras, you find a nice pattern in the series of natural numbers. And patterns in sets is my main interest, and therefore I want to go on from digits to shapes. One of the most simple patterns when you use shapes or tiles is maybe this one. And also this set of tiles can be divided in several sets. So just like the numbers odd and even, you can say, well, we've got black and white. And you see that never two black squares are connected with the edges and also the white. So this is a nice division of the set of square tiles into two sets. When you go one step further and you want to make a division like that of hexagonal tiles, you will see that, well, you can start making one tile black, but now the next one, the next black one, cannot be this one or this one or this one. Well, the first black square, hexagon, can be this one. So you end up with a division of the set of tiles in two groups, but still here, two white ones are connected. So you need a third color. So this is a next step in finding nice subsets of a certain class. You need three colors to color a system like this, and well, we all know the works of Escher, and he also knew that you need three colors to make a nice tiling with different colors of, so not connecting the same colors at the tiles. Now we've come to Escher. So my goal is try to understand patterns, and when you really understand patterns, you can do nice things with it. And well, as an example, I used this one of Escher, and I took just one part out of it, so 3 Chinese men, and I found out that when you divided this set into 3 pieces like this, you can just flip them over. And at the end, well, you don't have Chinese men anymore, but you end up with lizards. So I will turn them back one time to see the Chinese man. So this drawing of Escher is connected to this one. And that's because you understand the basic pattern. So let's go a little bit further with the patterns. I here have 3 layers which are interwoven, as you can see. When I take away one of the layers, these 2 layers are still interwoven. They are still connected. You cannot take them apart. When you compare it with another example like this, it looks almost the same. It's similar. But now in this case, let's remove one layer, and you will see that the other one is just on top of it. So there's no interwoven layers anymore. So let's put back one layer. So the light one is just laying on top of the dark one, and the dark one is laying just on top of this one, and this one is laying on top of this one. So which one is above? So you can end up with very interesting situations. Let's go back to the square pattern. When you start with square patterns, this is clearly an interwoven set of two layers, and you cannot take them apart. Also, Escher used this pattern very much in his tilings. You see here his design with fishes. Also in Escher's work you see a lot of combinations of fishes and birds. So I decided to make that combination also in this kind. So you can start with 4 fishes and just flip over the parts. And you see we end up with 4 birds, which is another drawing of Escher. So again, understanding the basic pattern makes it possible to make this beautiful transformations. And transformations, mathematics, the beauty of mathematics. Till now, we've seen some 2-dimensional patterns. We can go on to the 3rd dimension. Well, you can build a 3-dimensional object by just putting the squares of a square pattern into this configuration, as we all know. It might be interesting to know that also a pattern like this can be transformed in a nice three-dimensional system. Well, the way I can do it is like this. So you just slide all the squares together. You squeeze the complete pattern, so to say. And also here you end up with a set of cubes. So different kind of transformations that can be used to come from 2D to 3D. Three-dimensional objects, well, they are very much connected to two-dimensional patterns. Yeah, you can see say that this is a pattern, a tiling pattern, but now not on a plane, but on a sphere, like this one. So you see, well, in fact, three different types of tiles: triangles in this series here, square tiles, and pentagonal tiles, which you can use to build a tiling on a three-dimensional object. Also, Escher experimented with this kind of tilings, as you can see in this example. And well, I thought it could be interesting to find out how you can come from 2D to 3D. And I made this little animation in which you can see that you can start with just one strip of triangles to build the object that Escher used for his tiling. And now another thing is added to the three-dimensional art. It's the movement. So another dimension, you can say. So by just rolling up the strip, you end up with the icosahedron. There are more ways to create other objects, starting with just simple known objects. This is an example by Leonardo da Vinci. In a book, he made some illustrations of this kind of objects. But one interesting operation he illustrated is the elevation of an object. By elevation, he meant that when you've got one plane over here, one face over here, a triangle face, you can take the midpoint and pull it outwards and to create a new situation. When you pull out the midpoint of this face till you reach the situation that you've got an equilateral triangle over here, you've got pyramids on all of the faces. And so you end up with an object which is built also with only equilateral triangles, just like this one. Well, it's better to illustrate it with the real transformation, as you can see here. So a very nice way to create a new object, starting with an existing known object by applying a certain definition, a certain transformation rule that he posed. So now we've got this object, and well, we all know that with the use of only triangles, you can build a lot of different objects. And we like objects in which you use only one type of tile, you can say. My question was, at a certain moment, what are the other shapes of tiles you can use to build interesting objects? So, not a triangle, not a square, but, well, what kind of tiles are possible? So again, a mathematical question to try to create beauty. A transformation procedure I defined was this one. When I take just one of the pyramids and I turn it a little bit, then I get a new situation of the object. And at the moment I apply this transformation on all the pyramids, you get something like this. And now in each still of this animation, you've got an object which is built with all tiles, all equal tiles, but not the simple tiles like triangle, square, or hexagon. So this was a mathematical solution of an aesthetic problem. There are more transformations you can use to create new objects starting from known objects. A mathematical operation is called stellation. Stellation, well, it's quite easy to describe. When you start with a triangle, the triangle face of this object, you can enlarge the triangle, and when you enlarge also this triangle, you can see that when this one is enlarged and this one, at a certain moment they meet. So you've got a new edge. Well, it's better to illustrate it with the animation. So each of the triangle is enlarged, and now you see that they meet here to form a new shape. The shape is quite interesting because it is double layered, and you can see it when I open it up. I just take away some of the parts so you can have a look inside. And especially when I round off the corners a little bit, the complete object becomes more gentle. And you can see that just in a few steps, you create a very complex object, starting with just a simple object and a simple transformation rule. And interesting about this object is that it is still one layer. It has certain levels, but you see when I start walking here, I can walk here, I can walk through, and I end up here, but I started here. So these two faces are connected. So it's one single surface which is entwined by itself now. Also, Escher did some experiments with this kind of shapes. This is just a stellation of the dodecahedron, and well, also he opened it up to put the animals in. And well, this kind of objects is quite interesting. Also, when you try to find out how you can build this kind of objects. Also, this is stellation which I have opened up a little bit. But to try to find out what kind of operation you need to build this object, well, I can show you with the animation how it works. You see, the faces are not that complicated. But to put it together in a nice way, so that they don't touch each other, you have to slide them towards the center, but also rotate them a little bit. So a combination of two transformations. Again, the beauty of mathematics, I think. Also, this is a nice example, I think. This is a drawing by Escher again, and it's built out of two objects. A tetrahedron over here, and another one going through the first one. But you can also look at this object as an object built of small triangles, equilateral triangles again. So the objects then can be built with only triangles. And again here, you can unfold the complete object as one single strip of triangles. And to show how to assemble the object then, I made this small animation in which you can see that the movement itself becomes very important in the complete idea. It's just like dancing triangles. But with one single strip you can build complex objects like this. This shows essentially the beauty of mathematics, because there are some fundamental mathematical things involved here. And one of the things is duals, and the other thing is Hamilton paths. I won't go into the details, but that makes it possible to make animation like this. One other thing that's interesting, well, I showed you some a semblance of three-dimensional objects built with two-dimensional parts. And a lot of objects we see in the environment and we can buy are built with simple parts that are slid together. But when you look at all those objects, the way they are the sliding goes is very simple. And so I thought, are there more ways to slide objects together in a more interesting way? And inside this object, there's a little tetrahedron. So 4 triangles forming the shape. And this object is built out of 4 rectangles. And you can slide it together like this. It's not obvious that you can assemble an object like this with just 4 parts. But the trick is that you have to slide all the parts together at the same time. So you cannot put away one part, you have to put all the parts together at one time. But once you've seen this idea, you can enlarge it. I just doubled the rectangles, so now you can build into infinite a structure with just laser cut parts. The only problem is that you have to put all the parts together at the same time. So this is as far as we could get at that time. But the idea of sliding together simple parts, I developed it a little bit further using just paper. The advantage of paper is that you can add a folding line, and so you can build objects like this. And also just by sliding together the parts, as you can see here. So you can double the principle and make more interesting objects. And well, it finally resulted in objects like this. And I made this in steel. This is about 2.5 meters high. But it can easily be built. And well, these are just a few variations of what you can do with the same building blocks, the same units. So you can see the folded parts, and you can slide it together in any shape. So folding together parts, of sliding together folded parts resulted in more different objects. I will show you one more. So 2 elements are combined in this way, and when you go on adding more elements, you end up with structures like this. And well, I had a close look at this structure, and I found out that when you look at this structure, you see a certain simple pattern on the top, like here. And this again is just a normal tiling. So let's go back to the tiling. And well, there's more to say about this tiling, I think. The most important thing, I think, in this tiling is that it has a certain orientation. You can see this as, well, when you look at it as a windmill, it has an orientation like this. And you can change the orientation by just a very simple operation. So now the orientation is the other way around. And it looks a very small thing, but this is quite interesting, and I will come to it a little bit further. You can do this with more tilings, so also this one. You see there's a certain orientation in the middle, and you can change the orientation by this operation again. So it looks like you end up with the same tiling, but it's the mirrored one. And looking at this pattern, I came across a drawing of Leonardo da Vinci. And you here see the same hexagon and the same triangles around the hexagon. So I thought, that's interesting. He studied the same tiling, and this is just a small drawing on one of his notebooks pages. The drawing is over here, and you see more drawings of the same type. And I studied it a little bit further, and well, especially this one. You see here it's a tiling of rectangles and small squares. And so you can say, well, it's just a tiling, so like this. But when you look a little bit closer at the drawing of Da Vinci, you see that it's not just a tiling, it's the lines that are more important than the space in between. And the lines are drawn in such a way that this line ends up above this one. So it's laying on top of this line. And also here you can see this one is above this one. So it's not a tiling, it's more like a construction. But it's exactly the same pattern. So mathematically spoken, we're talking about the same thing. But in practice, when I translate it, I end up with this instead of a tiling. So a construction which is in fact a dome, which is quite something else. But you can recognize the rectangular shapes and the small squares, but now in a construction. Well, what does this mean? This is a construction which is very interesting because of the way you have to build it. So not the final result, but the process again. So the process in time is the interesting part of the construction. I start here by putting on a table 3 elements for the construction. You see that each element ends with the top of the element on one of the midpoints of the other one. So here again, a top on the midpoint of this one. So what I have to do now is to add here, but this one should be on top of this one. So I just have to lift the construction a little bit, and here I create the first step of my dome. So from this step on, I can add more, and well, you will see that the dome grows by adding more sticks, but adding sticks is always at the edge of the construction. So it's never a big deal, it's quite simple to build, and you end up with constructions like this. When I found this out, I went to Italy to make a real big one. And there was a sculpture park in the north of Italy that was very interested in the project, and they decided to collect beams of about 5 meters long. So I couldn't do it by hand anymore. The beams were far too heavy. But here we see, you see that I built up the construction in the same way as I showed with the small pieces. Just starting with laying one beam on another one. And well, I first had to build a little model because my Italian language is not that good. So I had to explain it in this way. But here you see that we are building the construction beam by adding beams. And the construction is growing. And here it's the height of one man already. So we ended up with a construction of, well, 20 by 15 meters and 2 meters high. So a real Leonardo da Vinci dome. And you see the beauty of the structure. And also in this one you can recognize the mathematical underlying pattern. Well, I started to develop this idea a little bit further, and now I come to the part that you can see that things like a FabLab are very interesting also for me because I first redesigned the beam, but the function is still recognizable. You've got 4 points, and each element can be connected from the end to the midpoint, and like this one. But these elements can be now laser cut or just milled by a milling machine. I started first with the milling machine. So from wood I made all the parts. You need a lot of parts to build real domes. But as you can see here, it's quite fun and very easy to build. I did this with students of all kinds of schools. This was a student project, as you can see here. The total construction is very stable, so you can just take the edge with all the students and lift it as a ceiling. After that came a question, posed by a mathematician, of course. He said, well, all the domes are always parts of a sphere. So, in fact, you always have positive curvature. Wouldn't it be nice to have also negative curvature in a dome? So not only this kind, but also this kind. And for me as an artist, this was interesting because those shapes are far more beautiful. And so I came out with this simple solution. Beside having an element in this shape, I added an element in this shape, so a hollow one. And with that, I built this dome. This was in Groningen, where I met Karsten Joost. And here I am building a dome with positive and negative curvature. So double curved domes. And this is a look from inside, so you can see that you can make beautiful architecture with this. And this is another one. So with just the simple system of laying one piece on top of the other, you can make a net, and this is quite stable, and it's a real nice dome. After that I went on trying to create more variations of the same principle. Again, 4 areas where the connections are. So one positive, one negative, one negative, one positive connection. So the basic idea of the Da Vinci element. But now in a shape that can be made with a laser cutter. I made this from paper and from other thin material. And you can connect one of those pieces very easily by plugging it into another one. This works with paper and with all kinds of materials. And this is a very nice way to make constructions. And you see here the paper elements, and you can make beautiful constructions. And here I used just another pattern, but the same system and the same elements. And after that, mathematically, the interesting step is then to transform the element and see what you get at the final result. So a simple transformation of the element, what's the result in the final construction? Well, this turned out to become a sphere. So with just 12 elements, you can build a sphere out of the elements. You can use different patterns again and build squares. So here I use a pentagon to start with, and it all comes to a sphere. Here you've got the 3 different patterns. You can go on, you can build it a little bit more or a little bit less. The transformation of the element, you can vary this very easily. And again, laser cutting the elements, you can create a sphere like this. Also with the same element, not only a sphere, but also a cylinder can be built. I've got an example over there, so if you're interested, I can show you. This is a very bendable cylinder. So with simple elements, you can make all kinds of variations, like you see here. coming back to the positive and negative curvature, it turned out that when you do that using these kinds of elements, you don't need two different elements anymore. Because when I've got this one with just a little bending in it, I can just turn it over and I've got the negative curvature. So these two are now exactly the same elements, but when you are going to build with it, you see the positive and negative curvature again. So with only one element, you build very interesting constructions. And at every point, you can choose between the negative and the positive. So it's your choice what kind of shape the end shape will be. Here are a few pictures. So again, the positive and negative. And this is just the shape of the elements, and you can see here to the top or to the bottom. It's your choice. Going a little bit further with the evolution of the shape, I ended up with the S form, so a double bending. And this resulted in, well, it's hard to expect to say now what you get as construction, but the double bending resulted in a double layered construction. So still it's a very simple connection. You just plug it in and you've got a stable construction. But now you see one layer and another layer here below. And each element is part of the underlayer and part of the upper layer. You can see it a little bit better. And when I was working on this one, I came back to the right-handed and left-handed turning of the tilings. I'm almost finished. When you look at the hexagon over here and the hexagon below, you see that it's just going the other way around. So here you're back to the right turning and left turning of the tilings. Well, this is the shape that's now on the exhibition. And here you can see the connection a little bit better. So this kind of structures are built with just simple laser cut elements, just plugged together, and you've got nice structures. Well, this is a final example I will show of the evolution of the element. By this transformation, I end up with double-layered spheres, and also those are at the exhibition. So now each element is part of the outer sphere and part of the inner sphere. So all kind of double-layer structures can be built with this principle. And well, you can make it as funny as you want, but well, let's end with this one. And well, that was what I had to show you.